This is my second video on how to integrate rational functions. A rational function is a quotient of polynomials. If you haven't watched the first example yet, I suggest you do that before continuing. In the first example, I explain things in more detail and more slowly. In this video, I will integrate this function. I want to compute an antiderivative of this function x to the fourth plus 1 over x cubed plus 2x squared plus x. My first step is going to be to make this a little bit easier by using long division and reducing the degree of the numerator. Long division for polynomials works the same way as for integers. If I have a quotient of integers, for example 17 over 3, I can do division. The quotient is 5 and the remainder is 2, so I can write it as 5 plus 2/3, and the advantage is that now the numerator is smaller than the denominator. So I can do the same thing for this quotient of polynomials to get a numerator with a degree smaller than the denominator. I won't write the details, this could be long, but the outcome is this. And indeed, the degree of the numerator is 2 less than the degree of the denominator. So we only have to worry about integrating a quotient like this when the degree of the top is at most 2. Next, I'm going to factor the denominator. In this case, the denominator factor easily. Now, I know how to integrate the quotient. This is just a polynomial. The difficult step is to integrate this part. And the idea is going to be try to rewrite this in terms of fractions of polynomials that we already know how to integrate. This step is sometimes called decomposition into partial fractions. And I'll repeat, what I'm trying to do is take this function and write it in terms of rational functions that I already know how to integrate. So with a denominator like those, there are already two functions I can think of quickly. I can consider 1 over x, because I know what an antiderivative of it is. And I can consider 1 over x plus 1, again, because I know what an antiderivative is. So, given that I like those two functions, perhaps it's a good idea to write this fraction as a real number a divided by x plus another real number b divided by x plus 1. If I succeed at that, great, because I will know how to integrate the right-hand side. Unfortunately, this is not going to work. And here is why. I can certainly reduce this to common denominator. I can make it have the same denominator as here. And then I will have a polynomial of degree 2 at the top. However, I only have 2 coefficients. And here I also have a polynomial of degree 2, and I have 3 coefficients. So chances are it's not going to work, it's not going to match up. I won't find real numbers of a and b that will make it work. And even if I do, it will be by accident. But I want a method that will work for any polynomial of degree 2 here. We already did long division to make sure the degree at the top is at most 2, and now I need a method that will work for anything with degree 2. In other words, I'm going to need 3 coefficients here. If I don't have 3 terms, it's not possible that it works. So I need an extra term, which means I need an extra function that I know how to integrate with a denominator related to that. And that function is 1 over x plus 1 squared, because this one is as easy to integrate as the other two. Specifically, an antiderivative will be minus 1 over x plus 1, because the derivative of this is minus x plus 1 to the minus 2. So let's add a third term. And now, yes, the common denominator will be the same one. At the top, I will have a polynomial of degree 2 with 3 coefficients, which therefore I can match up for any polynomial of degree 2 with 3 coefficients. I won't do the algebra. I invite you to do it slowly, maybe like I did in the previous video. And after doing it, the answer will be that a equals 1, b equals 2, and c equals minus 2. So we've done the algebra. Now let's go back and finish the integration. This was the integral I was looking at. The first step I did was use long division and factor the denominator to rewrite it as follows. Then the second step was to decompose this quotient in terms of simpler fractions. So all that is left is integrate this term by term. I know how to integrate a polynomial. The antiderivative of 1 over x is ln x. The antiderivative of 1 over x plus 1 is ln of x plus 1. And here the antiderivative is minus 1 over x plus 1. And don't forget the integration constant. And there we have it. This is the final answer. And this can be verified. You can take this function, compute its derivative, and see that it agrees with that one. It's an interesting process to do, because if you do that and then regroup terms to make it look like that, you will be undoing exactly each one of the steps we did to get to here.